Jai Hind everyone. In this lecture of the subject Electrical Machines 2 KEE 503, I am going to discuss the speed control of three-phase induction motor. I am going to discuss various methods of speed control of three-phase induction motor. The speed of three-phase induction motor, which can be seen, it depends upon the rotor speed of three-phase induction motor depends upon the frequency of supply given to the stator, number of poles P for which stator is wound, and the operating slip of the motor. So accordingly, the methods of speed control can be classified based upon whether we are controlling the speed by varying frequency, by varying the number of poles, or by varying the operating slip S of the machine. As I already mentioned, F is the supply frequency in hertz. It is frequency of supply given to the stator winding. P is the number of poles for which the machine is wound, and S is the operating slip of the motor. Here NR is giving us the speed in RPM, that is revolutions per minute. We can also write down the equation for rotor speed as NR, small nr, as twice F upon P 1 minus S. Twice F upon P is basically the synchronous speed in RPS. It can also be written as NS times 1 minus S. Here NS is synchronous speed in revolutions per second and NR is rotor speed in revolutions per second. In this expression, NR is rotor speed in RPM and it can also be written in terms of synchronous speed and slip of the motor, where NS is going to be the synchronous speed in RPM. So accordingly, the methods of speed control of three-phase induction motor can be classified as frequency control, pole changing method, and the slip control. There is another way of classifying the method. The other way is when we are implementing the control from stator side and if we are implementing the control from rotor side. So if we are implementing the control from stator side, the methods are supply voltage control, supply frequency control, and by changing the number of poles of the motor. If we are implementing the speed control from rotor side, the methods can be adding extra resistance in the rotor circuit of the machine, cascade control, and by injecting slip frequency voltage in the rotor circuit. Now let us come back to the previous slide. I have mentioned here that various methods of speed control are frequency control, pole changing method, and slip control. Let us compare these methods. Let us compare the methods mentioned over here with the methods mentioned over here. Here we can see that frequency control, second is pole changing control, third is slip control. We can very well see here that frequency control as it is appearing here. Number of pole changing by changing the number of poles as it is appearing here. Rest of the methods are actually the methods of slip control of three-phase induction motor. So let it be the supply voltage control, let it be the control by speed control by adding external resistance in the rotor circuit, let it be the cascade control, let it be the speed control by injecting slip frequency voltage into rotor circuit. All these methods are actually the methods of slip control for controlling the operating speed of the motor. So starting with the supply voltage control, what we can see over here is, as far as the speed equation is concerned, as far as this equation is concerned, the term voltage is not directly appearing over here, right? Actually, by varying the supply voltage, we are going to vary the operating slip of the machine, and accordingly, we are going to vary the operating speed of the machine. So, voltage control method, let us see the torque equation of the motor. Let us see what is the effect of varying the supply voltage on the torque produced by the motor, and let us see if there is a variation in the torque developed by the motor, how it is going to affect the operating speed of the motor, right. So starting with the torque equation, we know that the torque equation is given as m upon omega s, where m is the number of phases. If we are talking about three-phase induction motor, so for us m is going to be equal to 3. Omega s is the synchronous speed in radians per second. VE, you recall the Thevenin's equivalent circuit of three-phase induction motor. We have discussed it in previous lecture as well for the same subject. VE is the Thevenin's equivalent voltage. You can see this voltage from the equivalent circuit. For your reference, let me draw that equivalent circuit over here. The equivalent circuit was the resistance RE, Thevenin's equivalent resistance it was, reactance XC, Thevenin's equivalent reactance it was, and as far as the other side of the equivalent circuit is concerned, we had here the reactance rotor circuit leakage reactance JX2, and we had the variable resistance R2 by S, where S is the operating slip of the motor, and here this was the Thevenin's equivalent voltage, right. The current flowing in this circuit can very well determine. The torque equation actually came from the expression T equals to Pg upon omega s, where Pg is the air gap power, and that Pg was given by I2 square R2 by S, I2 square R2 by S. I2 is the current flowing in this circuit. For three-phase circuit, the total Pg can be written as thrice I2 square R2 by S. So it is simply the substitution of equation of current I2 in this equation of torque production, which is Pg upon omega s, which gives us the torque equation in this particular form. Now we know from the analysis of the equivalent circuit that we have done previously, we know that VE is proportional to V1. What is V1 over here? V1 is the supply voltage. V1 is the supply voltage given to the motor. So what we can see from this particular equation, how that torque is getting affected by the voltage, we can see that TE, which is the electromagnetic torque developed by the motor, is actually proportional to supply voltage square, or I can write it as V1 square, right. So let us consider the torque speed characteristic of the motor. It is drawn over here. First, consider the outer one. This characteristic is the torque speed characteristic drawn for rated voltage, rated frequency condition. Right now, we are not talking about the variation in frequency. We are only talking about a variation in the voltage. So I can say that the upper one characteristic is drawn for rated voltage condition, right? So the torque developed over the x-axis in Newton meter, the speed in RPM over the horizontal axis. You know that well that this point is representing the speed ns. Motor can never operate at the synchronous speed ns, and the this point is representing the zero speed. This is the starting point. This is the starting torque developed by the motor, right? We know that this is the maximum torque developed by the motor. Now, let us consider, as we concluded on previous slide, that torque developed by the motor is proportional to square of the voltage. Let us consider a reduction in the voltage. Let us consider a reduction in the voltage by 10%. So the new applied voltage is 90% only instead of being 100%, right? So now let us apply a voltage which is equal to 0.9 V, where V is the rated value. So this is actually representing 90% of the rated value. What happened because of this? As we know that torque is proportional to square of the voltage. So under these conditions earlier, let it be TE1. Earlier, TE1 was proportional to square of the rated voltage, where V was the rated voltage. Now, here the voltage is reduced to a value, say for example, it is V1, where V1 is 0.9 times of the rated voltage. So, I can write that the new torque produced would be equal to 0.9 V square, which can be written as 0.81 V square. So, let it be TE2. So, what is the difference between this and this? We can very well see that the torque developed by the motor got reduced by this much amount. Earlier it was 100%, now it is 0.81 of that value. That is, the torque developed by the motor got reduced by 19%. So, in this manner, now let us see how it is affecting the operating speed of the motor. To see the effect, we must know the operating point over the torque speed characteristic of the motor. Now, how to get that operating point? See, the purpose of motor is to derive the load connected at the shaft of the motor, right? Now, let us consider load can have any kind of characteristic. For example, here I have taken a load torque which is constant in nature. What does it mean? A constant load torque means irrespective of the operating speed of the motor, the torque developed by the motor will remain constant. The requirement of the load torque will remain constant irrespective of the speed. The requirement of torque by the load will remain constant. So, considering a constant torque load having this much amount of load torque requirement, right? We see that this load torque characteristic is intersecting curve 1 at this point. The load torque characteristic is intersecting the motor speed torque characteristic at this particular point, right? Intersection with this particular point gives the operating speed of the motor as N1, and intersection here actually gives the operating speed N2. What we can see? We can very well see that speed N2 is less than speed N1. So, what it implies? It implies that when voltage given to the stator winding of the motor is reduced, the torque developed by the motor gets reduced by square of the voltage, right? The torque developed by the motor get reduced as torque developed is proportional to square of the voltage. So, the new torque is 0.81 V square or 81% of the previous value. A further reduction in voltage given to the motor will cause a further reduction in the operating speed of the motor. Now, remember, by this method, we can only reduce the speed of the motor. We cannot increase the speed of the motor. Why so? Because continuously we cannot operate the motor at a voltage which is more than the rated voltage. If we want an increment in the operating speed of the motor, what we have to do? We have to increase the voltage. And in that condition, we are going to have the torque speed characteristic somewhat like this. We may find an increment in speed, but this kind of operation is not permitted. So, we can only reduce the speed by this method. We cannot increase the speed by increasing the voltage beyond the rated value. This method of speed control is not much in use. It finds some limited applications, and usually with single phase induction motor, we go for voltage control for speed control of the motor. In case of single phase induction motors which are employed in ceiling fans, the way of controlling the speed of that motor is by varying the supply voltage. Let us now move to the second method of speed control. It is the supply frequency control. So let us again recall the equation of motor. What is that? 120 F upon P into 1 minus S. We can very well see that the operating speed of the motor, operating speed NR of the motor is directly proportional to frequency. Let us assume other parameters in the equation to remain constant. So NR is directly proportional to frequency. What it implies? If we are increasing frequency, we will get a corresponding increment in the speed. If we are reducing the frequency, we will get a corresponding reduction in the operating speed of the motor. Now, when we are varying the frequency, this can be very well concluded from the speed equation of three-phase induction motor that a variation in frequency is directly going to affect the operating speed of the motor. But at the same time, only increment or decrement in speed is not all that is there. We have to see the effect of variation of this frequency upon performance of the motor as well, right? So, as far as the performance of the motor is concerned, here let us see the effect of variation of the frequency upon the torque developed by the motor, right? So, for this, let us consider the starting torque developed by the motor and the maximum torque developed by the motor. Let us consider the effect of variation of frequency upon the starting torque developed by the motor and the effect of variation of frequency upon the maximum torque developed by the motor. So, we can very well see the expression over here. It is the torque developed by the motor. For starting condition, you know that slip S is equal to 1. So, in torque equation, I have only replaced R2 by S by R2 only, as the operating slip S is equal to unity here, right? Now, we know that the reactance Xc plus X2 is usually much greater than the resistance Re plus R2. What is Xc? Xc was the equivalent reactance, equivalent Thevenin's reactance as it was seen from the equivalent circuit. Likewise, Re is the Thevenin's equivalent resistance from the equivalent circuit itself. So, in denominator, we can see that this term is quite high as compared to this term. So, what can be done for simplification of the equation? We can very well neglect, as it is appearing in summation in the denominator, we can very well neglect this term in comparison with this term, right? So removing this term from the denominator modifies the equation in this manner. What I have done over here, I have just taken the frequency term out from the term which are dependent upon the frequency. We know that Xc can be written as twice pi f Le. Likewise, X2 can be written as twice pi f L2, where L2 is the leakage reactance of rotor winding, Le is the Thevenin's equivalent leakage reactance, right? So, besides this, which other term is there which is dependent upon the frequency? It is Ns. What is Ns? Ns is synchronous speed in radians per second twice f upon p. It is. So, I have just replaced this Ns by twice f upon p. M upon 2 pi is as it is. V square is as it is. From this term, I have taken twice pi f common. So, twice pi f square Le plus L2 square into resistance R2, which is the rotor winding resistance per phase value. I can write down the torque equation for the starting torque developed by the motor in this manner. Deliberately, I have grouped VE and F over here. The F square I have grouped with VE. What is the purpose? We will discuss over the in the next slide. Then 1 upon F. So, if I see the effect of variation of frequency only, I can see that the starting torque developed by the motor is proportional to the cube of the is proportional to 1 by F cube, where F is the frequency of supply given to the motor. Likewise, we can determine the effect of variation of frequency on the maximum torque developed by the motor. So, this is the equation of the maximum torque developed by the motor. For getting this equation, you may refer the previous lecture of the subject where we have discussed the torque developed by the motor. If we neglect the stator side resistance, then I can very well modify the equation in this particular form, and later on further the equation can be simplified in this form in this similar manner what we have done with simplification of the torque equation at the time of starting on the previous slide, right. Now, let us see what happens when we are reducing the frequency, right. So, considering a reduction in the frequency from rated value, let us see the effect on torque speed characteristic of the motor. So, in this particular torque speed characteristic, F1 is representing the rated frequency. So, this torque speed characteristic is representing the characteristic drawn at rated voltage and rated frequency supply. Now, a reduction in frequency from F1 to F2, which you can see in the figure. A reduction in frequency from F1 to F2. It is going to increase the maximum torque developed by the motor, and the maximum torque developed by the motor is proportional to 1 by F square. It is going to affect the starting torque developed by the motor, and we know that the starting torque developed by the motor is proportional to 1 by F cube, right. Now, you see what happens over here. An increment in maximum torque from this value, an increment in starting torque. Let us further increase the frequency, let us further reduce the frequency to F3 value. It will cause a further increment in the maximum torque developed by the motor and the starting torque developed by the motor. A further reduction in the frequency will increase the maximum torque. It will increase the starting torque. The increment in maximum torque is by this relation, and the increment in starting torque is by this relation, right. So, this is the variation in the torque speed characteristic when we are reducing the frequency. Always see that it is the synchronous speed of the motor which is obtained corresponding to the rated frequency supply given to the motor, then it is corresponding to frequency F2. So, let it be NS2, let it be NS3, let it be NS4, and likewise let it be NS1, which is corresponding to the rated frequency of the motor. Now, let us see one more thing here which is very important. What happens to the flux when frequency is varied? We have considered the effect of variation of frequency upon the torque developed by the motor. Now, let us see one important aspect here is the effect of variation in frequency on the flux developed by the motor. For this, let us consider the voltage equation of the motor, the induced EMF in stator winding, right. So, E1 we know that given by 4.44 F NPH dash, where NPH dash is the number of effective series connected turns per phase. F is the flux per pole and F is the frequency, right. Now, this voltage is approximately equal to the applied voltage V1, right. Why so? What is the difference between E1 and V1? The difference between E1 and V1 is of the stator leakage impedance drop. That leakage impedance drop can be neglected in terms of the magnitudes of voltages E1 or V1. So from here what we see, this is a constant, this is a constant. So what we see is V1 can be written as proportional to phi and f. Now what we are doing over here, we are varying the frequency and we need to see the effect of this variation in frequency upon the air gap flux of the machine. So what I can do here is writing the expression for the flux can be written as V1 upon f. Now if frequency is reduced from rated value with constant rated voltage, the air gap flux increases. We can very well see the same thing from here. We are reducing the frequency, we are maintaining it constant. It will cause an increment in the flux developed by the motor. Now this flux actually causes saturation of the stator and rotor iron cores. This saturation is going to result in increased iron losses and distortion of the motor magnetization current. This distortion would be responsible for introduction of harmonics in the supply frequency, right? So an increment in the flux beyond this design rated value is not permitted during the speed control of the motor. So what we have to do? We want to reduce the speed of the motor by reducing the frequency of supply given to the motor, but at the same time the solution is to maintain the ratio V by F constant. So whenever we are controlling the speed by reducing the frequency below the rated value, what we have to do? At the same time, in the same ratio, we have to reduce the voltage as well, right? This will maintain the ratio V by F constant. A constant V by F ratio results in a constant air gap flux of the machine, right? Now, below rated frequency, supply voltage is also reduced, what I just told you, with frequency such that the ratio V by F is maintained constant throughout the operation of the machine. This is called the triple VF control of the motor. Triple V stands for variable voltage, variable frequency, right? So, variable voltage from frequency control, we moved to variable voltage, variable frequency control. Now, let us see what happens with this. So, below the rated frequency, voltage and frequency both are varied for the speed control of the motor. This is said to be the variable voltage, variable frequency control of the motor. Now, let us see the effect of the same effect of variation of frequency as well as voltage, but maintaining V by F ratio constant upon the torque developed by the motor. For this, we may need to refer the previous slide, right? Now here, what it was, the starting torque developed by the motor was proportional to this, right? Now from here, what I can see, I am maintaining V by F ratio constant. So, with this constant, I can now write that the starting torque is going to be proportional to 1 by F, because V by F term is now constant, right? Now further, in the similar manner, let us see the effect on the maximum torque. What we can see, that maximum torque expression is containing the term V by F square. V by F is maintained constant. So, with a variation in the frequency, there is no variation in the maximum torque developed by the motor if we are implementing variable voltage, variable frequency supply. Agreed? The same thing is depicted over here. So what we concluded right now? We concluded that TEM will remain constant. TEM will remain constant. TEST would be proportional to 1 by F. So a decrement in frequency, synchronous speed here is ns1, corresponding to this it is ns2, here it is ns3, ns4 and so on. The torque speed characteristic, this line is representing the maximum torque developed by the motor, right? This is the starting torque under first condition, second condition, third condition and fourth condition, right? What we can see over here, maximum torque will remain constant. With a reduction in the frequency, we will find a corresponding increment in the starting torque developed by the motor. Now, when frequency is increased, the flux will get reduced. Why? Because we have written phi proportional to V by F, right? If we are increasing the frequency beyond rated value, if we are increasing the frequency beyond rated value, we will find a corresponding reduction in the air gap flux of the machine. If we are maintaining this constant, we have to maintain this voltage constant. Why? Because we are now increasing the frequency beyond rated value. Voltage V is already at its rated value. We cannot continuously operate the machine with an increased voltage beyond the rated value. So, we don't have the option of maintaining the V by F ratio constant, right? So, when we are controlling the speed of the motor beyond rated frequency, I mean to say when we are increasing the speed of the motor by increasing the supply frequency beyond rated value, we have to maintain voltage V constant at the rated value, right? So, when we are maintaining V constant, we are only increasing the frequency, we are going to get a reduction in the air gap flux developed by the motor, right? So, what would be the effect of this on the torque speed characteristic? Now, let us see what would be the effect of the same on torque speed characteristic of the motor. Let me plot the new torque speed characteristic beyond this range over here, right? So, what I know that TEM is proportional to 1 by F square if V is kept constant, right? If V is kept constant, TEM would be proportional to 1 by F square, TEST would be proportional to 1 by F cube. What we are doing over here? We are actually increasing the frequency. So, we will find a corresponding reduction in the maximum torque developed by the motor. Likewise, we will find a corresponding reduction in the starting torque developed by the motor. The reduction in starting torque would be more as compared to the reduction in the maximum torque, which is evident from these two expressions. Now, let me plot the characteristic. So, let me plot the torque speed characteristic. I have reduced the maximum torque, I have reduced the starting torque. This corresponds to some frequency which is more than the rated value, let it be f2 dash. Let me draw the axis as well for more clarity, right? So, let me draw another characteristic with further reduction in the frequency, with further increment in the frequency. Let it be f3 dash. Let me draw another characteristic. Starting torque will get reduced further, maximum torque will get reduced further, and this corresponds to f4 dash, ns4 dash, ns3 dash, ns2 dash, right? So this is the effect of variation of only frequency beyond rated value upon the torque speed characteristic of the motor. So we can conclude that by reducing the frequency, we will reduce the operating speed of the motor. By increasing the frequency, we will increase the operating speed of the motor, and at the same time, we have to take care of this effect of this variation in frequency upon the torque speed characteristic of the motor. We have to take care of the effect of this variation in frequency upon the air gap flux of the motor as well. The next method is the method of pole changing. In the method of pole changing, the three methods are: we can change the number of poles by multiple stator windings having different number of poles. We are having another way of changing the stator poles as the method of consequent poles, and one more method is there which is said to be the pole amplitude modulation for varying the number of poles of the motor. So let us consider the very first method first. So with multiple stator windings having different number of poles, actually the stator is wound with more than one winding, right? So by providing the stator with independent windings, for example, for a two-speed motor providing two windings, each designed with different number of poles. So a total number of 6 terminals would be brought to the terminal box of the machine. Out of these 6 terminals, 3 terminals correspond to the one winding and rest 3 terminals correspond to the other winding which is wound for another number of pole, right? Changeover between the two windings is done with the help of a TPDT switch. TPDT stands for triple pole double throw. One throw of the switch will connect one winding, another throw of the switch will connect another winding. The winding which is not in use is actually left open circuited to avoid any kind of circulating current and the subsequent heating in the machine. So, if suppose we have got two windings, one for 4 number of poles, another for 2 number of poles. So, while operating the motor with 2 number of poles, we have to leave this winding open circuited. Method of consequent pole comes next. Stator is provided with one winding, but what is important? Provision of reconnection of the coils, right? The principle is explained with the help of a winding having 4 turns only. Direction of current is from A to B and from C to D. This is the case which we are considering here. We have got 4 coils over here. These 4 coils or turns are connected in a manner. Coil 1 and 3, turn 1 and 3 are connected. Likewise, turn 2 and turn 4 are connected in series. Turn 1 is connected like this. Turn 2 turn 4 are connected like this, turn 1 and turn 3 connected like this. Right now we are considering the case where direction of current is from A to B and from C to D. We need to combine these two sets of coils shown over here. So how are we combining them? We are combining them so that the current direction is from A to B and from C to D. So what I have to do? I have to connect terminal B with terminal C, right? We can see it in this manner. It is showing the direction of current in the two sides from A to B, from C to D. We can either have series connection or the parallel connection of the coils. It results in 3, 4, 5, 6, 7 and here comes the 8th S, right? It results in 4 generation of a field having 4 number of poles. Here the direction of current is changed. From A to B it will remain same and in the other group the current is flowing from D to C. The number of poles so produced are 4. So 2 pole pairs are produced. It is giving us a 4 pole winding. It gave us an 8 pole winding. And we know that NR is NS into 1 minus S, that is 120 F upon P into 1 minus S. We are varying P, keeping other terms constant. So it will vary the operating speed of the motor. So that's all for this lecture. Thank you.